So our next speaker is Brad Holden of UCO Lick, and he'll be presenting on ideas and concepts for a new LRIS.
Hi, everyone. My name is Brad Holden, and I'd like to also thank the organizers for giving me the opportunity to present this. As my title is, we're talking about ideas and concepts for new LRIS. LRIS is a first light instrument on the Keck 1 telescope, and it's showing its age. So we're thinking about how we're going to move forward with a new instrument that fills the same sort of role. So I'm not going to give you a concept design or anything like that. This is much earlier in the process, and the reason why I'm giving this presentation is I would love your feedback. I would love to hear from users of LRIS what they think is important at the beginning of the design process so that I can learn from you what we should be including. So what is LRIS? Obviously, the name is the Keck Low Resolution Imaging Spectrometer, and on the right, I show everyone's favorite GUI interface to the LRIS spectrograph. And the great thing about LRIS, the reason why it's a first light instrument that we're still using 27 years later and is in demand 100 nights per year, is that it's a very flexible and efficient spectrometer. The instrument is very configurable. It has a large number of mechanical subsystems, and those mechanical subsystems let you configure the instrument in a way to do the science that you need to do. It also has this elegant off-axis collimator design, which means that it views an image of the telescope focal plane, a piece of the field of view of the telescope, very far from the optical center of the telescope. You can actually see that in the GUI. And that was very efficient, and it was very pretty from a sort of design standpoint, but it has certain side effects. So if it's such a great instrument and it's in use 100 nights a year, why are we thinking about replacing it? Well, all these mechanical subsystems mean that it has a large number of mechanical failures. It is the most problem child of all the instruments on the summit of Mauna Kea. You have to do more repair work on it than any other instrument. And the way it's designed, it's mechanically unstable. In the plot on the lower right, I show the flexure of an optical image on the detector and how far it moves in arc seconds, both in X and Y, as you rotate the telescope through various position angles and slew the telescope in elevation. And you can see that an image would move on the order of 2.5 arc seconds. Finally, the off-axis location of the field of view constrains the image quality because of the way the telescope is designed. So you have basically a floor from astigmatism on how good an image you can get. So how can we do better? How can we make an instrument that meets many of the needs that LRIS meets, but is actually uses modern technology to do better in all the ways that we perceive it needs to be done better? Well, the obvious thing is, of course, VPH gratings and modern coatings that we use on KCWI. But there are other things, such as that in the image on the right, there's this new technology called freeform optics. And so the image on the right is an actual design for the WFOSS spectrograph that we propose to put onto the 30-meter telescope. And the great thing about that telescope, or that instrument design, is that it breaks the collimator into multiple pieces, and thus we can image on axis. This makes the spectrometer two things. It makes it on axis, which is good, but it also puts it much shorter because you don't have to have the collimator in a long distance away and then send light that same distance back. You break the collimator into multiple pieces, so the light travels the same physical distance, but it's much more compact and folded up on itself. Because it'll be shorter and more compact, it's more mechanically stiff, and we have much better understanding of how to make stiff designs, mechanical designs now. So we can do a better system. And we have a lot of heritage in history in doing that as well with ESI and MOSFire, where they have open loop flexure compensation systems. Finally, we would probably like this system to be ground layer adaptive optics ready. And that requires designing that in at the beginning. But if we do that and put it on axis, then we can potentially take advantage of all the best image quality that the Keck telescopes can deliver. So what we plan on doing in the coming year is we're going to deliver to the Keck SSC a report, and it's going to have science drivers. It'll have some sort of instrument baseline, and then we will do some concept development. We'll try and come up with an idea with some optical design and make sure it'll fit within the sort of reasonable cost constraints, and also, just as importantly, physically fits on the back of the telescope. So example science drivers I'm giving here, these are all LRIS papers, most of which were published in the last couple of years. And the amazing thing about this is that it uses the full range of LRIS capabilities. The image of spectra on the far right, it uses the mass capability, the multi-object slit capability. The spectrum in the upper middle panel uses the reddest parts of the spectrum, whereas the image in the upper left uses the bluest parts of the spectrum. So you have people using the full wavelength range of LRIS, the multi-object capability, and the lower right panel is the wildest thing I found. This is a moon of the Earth-Moon system. It's an asteroid that was captured and will leave the Earth-Moon system in a couple of years. But they were able to use the multiple cameras to take images in a wide range of passbands from the very blue to the very red. So using those science drivers, just the ones I would list from that previous slide, I can write down a set of instrument baselines, and this is what I would come up with. But this isn't necessarily what we want to do. But however, all of these constraints, all these things that you might want to do, fields of view, multiple detector systems. I've already had suggestions for 3 or 4 camera and detector systems, VPH gratings, GLAO. They're expensive. The complicated mechanical drawing on the right is the VPH system for KCWI. We would have to design something as complicated as that. So what I'm asking for you is, do you have answers to these questions? What sort of priorities should I assign to these various requirements? And what sort of capabilities would you like? So if you do have answers to these questions, please come to our breakout session today, or send me email, or use the Slack channel. Thanks.
Very good. Okay, we have some time for questions. So and I haven't followed this well enough, but the VPH gratings are able to give a reasonable wavelength coverage so that you expect that you could use them and still have the full wavelength coverage that people have taken such advantage of with LRIS.
Yes, VPH gratings are amazing. You can get the full wavelength coverage, but you can also do things like get a much higher ruling density than you ever could with a mechanical grating. So the advantage of that is that you can imagine doing much higher resolution. If you look at KCWI, they have R of 20,000 with certain combinations of gratings and apertures, because you can get ruling densities of like 4,000.
So we have questions from Josh starting out. What are some of the pros and cons of a Mossfire-like configurable slit mask for LRIS 2, or even if that's being considered?
The pros of that would be that you can get rid of the whole milling facility. The cons are that all the cons that you currently have with the Mossfire facility. Presumably, since it wouldn't be cryogenic, it might be more flexible. And, it's one of those things that's sort of in the back of my mind. It's certainly worth investigating.
Another question from Michael Bolte. What efficiency improvements are likely possible compared to the current LRIS?
Well, the VPH gratings give you a huge efficiency improvement. I imagine that modern coatings with their oftentimes almost 99% reflectivity across wide passbands would give us a big gain. I think the integrated numbers we're talking about are 50% improvements of a percentage. So that's kind of a funny way to think about it. But.
Okay. We have to move on. There's another question available, but if you could ask that in the Slack, and I know there are another couple Slack questions already posted. And as well as Brad said, there's a breakout session on this topic as well. So thank you, Brad.